Hey everyone, let's finish up simple harmonic motion by looking at some of the graphs that you'll encounter on the AP test. Here are the problems we're going to work. I'm going to page through them. I want you to pause the video and work each one out as best as you can before I do them with you. For our first problem, we have a 2 kilogram mass oscillating at the end of a horizontal spring. The horizontal position of the mass as a function of time is given, as shown above in the graph. What can you determine from this information? All right, well, first off, I'm going to draw a little picture of what's going on. So here's my mass, because a picture always helps me. And so this would be the equilibrium position 0, and it looks like it's oscillating between about, there seems to be about plus 0.25 and negative 0.25 meters. So hey, so this is the amplitude, right? Here's the amplitude. Our time period is about 2 seconds. Okay, what else can we find? Well, at the amplitude, at the far ends, the velocity would equal 0. So velocity equals 0 here, and velocity equals 0 here on the ends. That means that the maximum velocity is here at the equilibrium. So V max would be here at these spots in the center. In fact, let's go ahead and draw a graph of this whole thing and see what we get. So I've printed one off with just the oscillating x versus t graph. And so what would our velocity versus time graph look like? So we know at the amplitudes we have to have a 0 velocity. So we got to have 0 here, 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 here on the ends. And we know we have to have maximum velocity when we're at equilibrium. So we're at equilibrium here, here, and here. So we're at equilibrium here, so we have to have maximum. So this is a positive slope. So that's our maximum positive velocity right here. So that'll be up here. And then over here we'd have our maximum negative velocity. Okay, so that would be down here. So we're going to oscillate between these points, and we should end up with a sinusoidal graph, something like that. Don't worry too much on the AP test. If your graph looks kind of crappy, you can always just put, right to the side, it's a sine wave. Sine. Okay? And that'll help them understand what you're trying to do. All right, so what else? How about acceleration? So we know that when we're at equilibrium, our acceleration is 0. So we should have a 0 here, a 0 here, 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 here at equilibrium. And we should be at maximum acceleration when we're at our maximum displacement. So when this thing is at its maximum negative displacement, the spring is pulling it back towards equilibrium, so it should be a positive acceleration. So it should be here, 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 here. Uh-oh, I messed up. Here, and here. So this should be sinusoidal, or I guess in this case it's a cosine wave. All right, so it should look like that. That's what our acceleration should look like. All right, but what about our kinetic energy? Well, kinetic energy is 1/2 mv squared. So wherever the velocity is maximum, we should have maximum kinetic energy. And it's squared, so it shouldn't matter whether it's positive or negative. So I have a positive maximum here, and I have a negative maximum velocity here, which gives me another positive kinetic energy. And then I have another positive here, here, here. Those are my maximum kinetic energies. And then here it's not moving, so it should be 0 kinetic energy at these points. So I'm going to get a curve that looks like this. I want you to notice it never goes negative. And I also want you to notice that this thing completes 2 cycles for every 1 cycle of the other. So it's like twice as fast oscillating kinetic energy. What will the potential energy look like? Well, the potential energy has got to add up with the kinetic energy to add up to the total, which should be constant. So here's my total down here. It's easy. It should look like that. Constant all the way across. So our potential energy should be the opposite of this one. It should be maximum where this one's minimum, and minimum where this one's maximum. So it should look just the opposite. Okay, and that should make sense because when we're at our maximum position, we should have maximum potential energy. And since spring potential energy is 1/2 kx squared, again, we should have no negatives. And when we have a negative position, it gets squared, so we get a positive maximum. So it should look kind of like this. All right, and there you go. That's a lot of curvy lines. But they're not that hard to figure out. Do like I do on the test, which is just give some points where you know it's got to be, and then just fill it in, and you'll do great. So what else can we figure out? Well, we know the time period is 2 seconds. We figured that out already. So time period for a spring is 2 pi square root of m over k. And we know the time period is 2 seconds, and we know the mass is 2 kilograms. So if we plug all that in, we can find the spring constant. And I calculated that earlier to be 20 newtons per meter approximately. All right? Let's see, what else can we figure out? Well, we know that the spring force equals kx, and we know that the maximum amplitude is about 0.25. Okay, so x max equals 0.25 meters. So we can find the maximum force by plugging that in and what our spring constant is, which we just got. So the maximum spring force that we'll get while it's oscillating back and forth when it's at the ends will be approximately 5 newtons. Since we know what the maximum force is, remember that F equals ma. So with our maximum force, we can find the maximum acceleration. And so if we plug in 5 newtons here and our 2 kilogram mass, we can find that our maximum acceleration would be 2.5 meters per second squared. Can we find out the maximum spring potential and kinetic energies? Well, I don't have any velocity information, but I do have what the max amplitude is. So for the spring potential energy maximum when we're out at the end, that would be 1/2 kx squared. Plug in our spring constant that we got from above, plug in our max amplitude that we have here, and we would get a maximum spring potential energy of 0.625 joules. And we know that energy is conserved, so when the spring potential energy is 0 at the equilibrium spot, then we know that's what the maximum kinetic energy has to be, 0.625 joules. It has to be the same. And finally, since we know that that equals 1/2 mv squared, and we know the mass of the object, we can find the maximum velocity by plugging in that information, and that's 0.79 meters per second approximately. That's a lot of information from one graph. All of this information, all of this information. Well done. For our next problem, we have a pendulum that's got 10 kilogram mass at the end of a string swinging back and forth. This time they gave us a velocity time graph. So let's see first if we can figure out where the equilibrium and where the amplitude positions are. So remember that a pendulum will swing fastest here at the equilibrium. So therefore, at the fastest point right here, these are the equilibrium spots right here. That's where we're at equilibrium. And so that means that when we're at the far end, we'll have a 0 velocities on the end. So wherever we see a 0 velocity right here, that will be the amplitude. So the amplitudes are here, and the equilibrium positions are here and here. Another thing we can find out from this graph is that the max velocity is approximately 0.8 meters per second. So we have that going for us. Another thing we can see is that this graph is a little more choppy than our last one, but we can tell that this is approximately 1, 2, 3, 4. The time period is approximately 1 second, because in 4 seconds there's approximately 4 complete waves. And since we know that this is a pendulum, time period for a pendulum equals 2 pi square root of L over G. And assuming that we're on Earth, we could plug in our time. We can plug in G for Earth, and we'll get a length of our pendulum that's going to be approximately 0.25 meters. Okay? So We're cooking along pretty good. What else can we figure out? Well, we know that the kinetic energy is related to the velocity, so our kinetic energy maximum will equal 1/2 mv squared. We know what our kinetic energy is. We know what our max velocity is. And so if we plug this in, we'll get a maximum kinetic energy of about 3.2 joules. Now, that's here. Kinetic energy equals 3.2 joules. At the ends, our spring, not spring this time, our gravitational potential energy, which is mgh, will have to equal 3.2 joules as well. So we could figure out what this height is here. Or on the AP test, they usually use delta y. So what this delta y is. So if we plug that in, knowing the mass from above, knowing that we're on Earth, knowing that the maximum potential energy here has to equal the maximum kinetic energy at the bottom, then we can find that the delta y right here is going to be approximately 0.033 meters. And the last thing that I want to point out is that if we use this triangle right here, realizing that this is the length from here to here, and that from here to here will be L cosine theta for this side, and that our delta y will be this distance from here to here. So knowing that delta y equals L minus L cosine theta, and knowing that we already calculated the length, and we have the delta y, we can calculate the angle theta that we started from, which will be approximately 30 degrees. And there you have it. Problem number 3 gives us 2 different blocks oscillating at the end of identical springs. That means that the K spring constant is the same for both. The position as a function of time is given for each. Which block has the longest time period? All right, well, that's pretty easy. The time period over here is 4 seconds, and the time period over here looks like its time period equals 2 seconds. So the answer is that would be block Y. Which block has the largest amplitude? That also is easy. You can read the amplitude right off of here. From here to here is our amplitude. The amplitude over here is 20 centimeters, and the amplitude over here is only 5 centimeters from here to here. So that, again, is the largest is Y. All right, which block is more massive? All right, so we need some equation that has mass in it. So we know kinetic energy equals 1/2 mv squared, but I don't know the velocities because this is not a velocity time graph, so that won't help us. How about, hey, we know time period. Time period equals 2 pi square root of m over k. Now, this is the same spring constant for both. So therefore, what we have is that time period is proportional to the square root of the mass. And this one has twice the time period. So this one over here has twice the time period. So that means this one has to have 4 times the mass. Square root of 4 is the same as 2. So that means which block's more massive? Well, that again would be block Y. It's actually the mass of Y equals twice the mass of X. Problem number 4 gives us a kinetic energy versus time graph. And this time we have a 3 kilogram mass oscillating back and forth at the end of a spring. And let's see what they ask. What is the time period of the spring mass system? Now watch out. We are tempted to say that this is one time period, 3 seconds. But let's take a closer look at this. When we have maximum kinetic energy is when we're at the equilibrium, right? That's the equilibrium point. So we're here at 0 seconds, and then it goes all the way to 0 energy here. So this must be one of the amplitude points. So this is 1.5 seconds. And then it rockets back to equilibrium, and that would be over here at, what is that, 3 seconds. And then it goes all the way back down to 0 energy at 4.5 seconds when it's at the other amplitude. And then it swings back towards the center at the equilibrium right there at 6 seconds. So it's a full 6 seconds before it has reached one time period. So this is an entire time period. So please be careful. The kinetic energy and the potential energy graphs operate twice as fast. They go through one cycle in a half a time period. So our time period is all the way out to 6 seconds. So part B asks us, what's the potential energy of the system at 2.5 seconds? So 2.5 seconds is here, so I'm going to go up, and it's that dot, and I go over, and that looks to be about 0.77 joules. Well, we know the maximum right there is 1 joule. So if I subtract 0.77 joules from this, that's going to leave me with 23 joules, and that must be the spring potential energy at 2.5 seconds. How can the amplitude and the maximum velocity be determined? Well, let's see. We know that the spring potential energy equals 1/2 kx squared, and we know that the maximum spring potential energy will have to equal 1 joule due to conservation of energy. Whenever the kinetic is 0, the spring potential must be 1. And so if we set that equal to 1/2 kx squared, and we know the spring constant, then we can find that x, what their x max is going to be from that. All right, that's how we would find it. We can find the maximum velocity using kinetic energy. Kinetic energy equals 1/2 mv squared, and our max velocity will be at max kinetic energy. And we know the max kinetic energy is 1 joule again, and we know the mass right there. So mass, kinetic energy, we can find V max that way. Our last two questions are lab-based graphing problems. So we have a group of students that are tasked with finding the gravitational field strength, G, acceleration due to gravity, of the Earth using a pendulum. The students measure the time period of the pendulum as they change the length of the string and plot the data. So they're changing the length and measuring the time period. So as you can see, this would be on the x-axis, this would be on the y-axis, just like we have up here. Question is they didn't put anything down here. What goes there? What quantity did they graph on the horizontal part of the axis to make this linear? Well, let's see. Here's our equation. Let's put it in y equals mx plus b format. So time period, and we have 2 pi over the square root of g, and then we have the square root of L plus 0. So if we graph time period on the y-axis, which they did, and if we graph the square root of L, so if we put the square root of the length here, then when we get this slope, if we find it, the slope m should equal 2 pi over the square root of g. All right? Now let's take a look at our second one. It says a group of students are tasked with finding the mass of an unknown block, and they attach it to several different springs and measuring the time period of the block as it oscillates. So they're changing K, and they're measuring the spring time period. So this would go on our x-axis, this would go on our y-axis. But again, we have a nonlinear equation for a spring, so y equals mx plus b. Let's put, this is going to go on our y-axis. Our spring constant goes on our x-axis, but that's in the denominator. That's 1 over the square root of k. And then everything else goes here. 2 pi over this times the square root of m plus b. So if we put this, graph this on the x-axis, graph this on the y-axis, then this should be our slope. So if we put 1 over the square root of k, and then this time our slope will equal 2 pi square root of m. That's it. We're done.